Hello and welcome to my talk called NIM Move Semantics. I'm Andreas Rumpf, the inventor and lead developer of the NIM programming language. And so let's start with a few words about NIM. NIM's unofficial motto is copying bad design is not good design. However, nowadays there is a new buzzword that I can claim to adhere to, and that is we strive to reason from first principles and not by analogy. So we don't try to do what the others do, we try to do the right thing, starting with the foundations of computation. So NIM is a high-level general-purpose programming language that compiles to low-level code. We'll see how this works in detail in this talk. NIM has an indentation-based syntax inspired by Python and Ada. The type system has been inspired by Ada, and it's a systems programming language, whatever that means. In fact, what it means will be seen in this talk. So we now talk about move semantics. So the motivating example is this code. I start with a variable some numbers, and it's a sequence of integers, and sequence is like C++ is vector, so it can grow. It's an array that can grow in memory. I start with the numbers 1 and 2 inside this array, and then I append the number 3 in line 3 to it. Okay, now the question is how is this implemented? And here is the general implementation. So we have the variable some numbers, but that contains 3 fields: a length, which is currently of value 2. It has a capacity of 2, and then there is a data pointer pointing to a block of memory that contains these 2 numbers. And now, since the capacity is the same as the length, if we want to append the number 3 to it, we need to perform some work. Namely, we need to create a fresh block of memory, fill the values 1, 2, 3 inside them, and then we set this data pointer to the new block of memory, and we should invalidate the old pointer. So what we really want to do is to free the pointer to the old memory immediately, because that's the best behavior for the memory consumption of your program. And now if we free this pointer immediately, the problem is what happens if this pointer has been copied. So here is an example showing this problem. I start with the numbers 1 and 2, and then I copy this array into the other variable. Or maybe I create an alias. So for right now the question is what should this do? The case to watch out for is that other contains a dangling pointer, which we already freed. That would be a disaster for safety. So there are a couple of solutions how to avoid this problem. So the first solution was kind of outlined by me. We create a new sequence with the same elements, and we deep copy this thing in line 2. Which is nice, because then the code is easy to reason about, because now if I now mutate some numbers, I know the other sequence won't be affected. So this is what kind of like what functional programming also argues for, that the spooky action at a distance caused by mutating alias pointers is really hard to understand. So but we can also say, so some numbers must be changed, like it must be a pointer to a pointer, and then when some numbers points to a new block of memory, other can still point to this old block. And then some reference counting or garbage collection mechanism can clean up once other leaves the scope, for instance. So that's basically C# and Java solution. You can also say, well, this assignment shouldn't be allowed, like you need to say clone these numbers explicitly, which I think is a bit messy to work with. But it's also a valid design choice. And finally, the fifth solution might be, well, let's move these numbers into other, steal the memory, and then let's see what happens. So this is what you can do in nim as well. You can say other, move some numbers into other, and then afterwards some numbers is empty. So if you append the 3, this is the only number in there. So it's this destructive read operation. And since it's explicit in the code, we consider this to be totally acceptable. I mean, likewise, I could set the length of some numbers to 0 to deal with this. However, this is a destructive read, and so this is kind of like a performance thing to do, really. It's not like you want to use it all the time. But there are many cases where this move can be inferred and maybe be implicit. So this is the primary example, like say the function f creates a result for me, and since it creates it, I can move it into A because it's a new object, and we know new objects cannot be aliased. So, but more generally, you can also move from a location that is not used afterwards. So this is this last read, and in C++ it's called the expiring value. So here in this example, I rely on nim's move semantics to perform the move. So we start again with a sequence 1, 2, 3 in X, and then since after line 2 X isn't used anymore, it's moved into the Y, and likewise Y isn't moved after line 3, so Y's content is moved into Z. So no copy is performed. So this works well when the compiler can reason about the locations. Like local variables are a primary example where it's very easy to reason and to analyze the situation. But unfortunately, programming is more complex than dealing with local variables. So here I have an example where I outline how a hash table put operation might look like inside. So this var keyword in line 1 now means this table is mutable, like I can store into it. And the goal is to store the key value pair into this table. And the value is also a sequence of integers. So again, we have the problem here, what to do with this more complex object. So, and in line 3 now we say tables t dot slots at position h becomes this value, and we cannot perform a move here because value is a parameter that's passed to us, but we don't own the memory, so we don't know if this is used afterwards or not. Whereas when you take the bigger picture and see how it's used in line 5 and 6, you can see, oh, wait a second, values isn't used afterwards, so I could move values into the table and could avoid the copy. So, but this crosses the function call boundary, and we try to avoid heavyweight optimizations that rely on inlining too much. So the idea is to make the compiler help make the programmer help the compiler a bit out here. So if we annotate this parameter with a sync keyword, then the compiler knows that value is owned by the system. Like it's owned inside the put function. And since it's owned and it's the last usage of this owned value in line 3, it can move it. So we get the move in line 3 this way. And now the property of I want to take ownership of this value is passed onwards into line 6. And here now the compiler has to analyze and see, okay, values isn't used afterwards, so I can pass values directly to put without a copy. But sometimes this can fail. Like in this example, I use values afterwards. I mean, I echo it to the standard out. So the compiler has no chance, and it needs to create something that is a single owner. So what it does, it creates this copy of values and passes it to put. But it will produce a warning. It will produce a warning saying passing a copy to a sync parameter, because now we have a copy that's not visible in the source code. Okay, but this example can be fixed. If we get more move semantics by moving code around, funny pun. So if I echo the values first and then put it into the table, again it's the last usage of this values. Values variable, and now I get the move and no copy. So that's a good solution. And the principle in play here is that these sync parameters are optimizations. So if you get them wrong, nothing bad happens, but performance might suffer. However, that's not completely true, because you can also disable the copy operation. And then the compiler would complain, like, you require me to move this value here, but I cannot move it because it's not the last usage of this value. And I cannot copy it either because you've forbidden the copy operation. So go fix your code. That's also a possibility. Okay, so here I have a couple of more examples to get a feeling of what a sync parameter is and how to use it. So I have 4 operations, like putting a key value pair into the table, equality on a type T, plus operation on a type T, and appending a value T to a sequence in line 7. And the question is, which of these parameters should be sync parameters? And the answer is whenever it kind of lives on afterwards, like the value is put into an array or a table or some container. So this is my solution here. So appending to a sequence in line 7 should definitely have the sync parameter here so that we can move it. And in line 1, the key value pair should also be syncs. However, the key is actually questionable, because you might, when you do this is in the table override operation, where it looks like, do I know this key already? And if so, I update its value. But if it's a new key value pair, I also store the key and the value. So this depends a bit on what is more likely. Is it more likely that the key is known to the table or not? So if you want to be conservative, only make the v here the sync parameter. Okay, so this is about getting values, moving values into containers. Like, this is construction. We construct the data structure. There is a related problem, and that is getting values out of a container, landing a value. So here I have the table, hash table get function outlined again, and result represents what we were going to return, and again the problem is here that we have a copy, because we do not know if t.slots at position h is used afterwards or not. Okay, so now you can say, yeah, let's move it, and then the compiler will tell you, no, you can't move it, because t.slots is immutable, because t is immutable. It's an immutable parameter. Okay, so then you can say, yeah, okay, so make it mutable, right? But now it's clear that, hey, we are mutating the table, like a read access mutates the table. And that doesn't seem like a good idea. I mean, you can do it, like you can move it out of the table, and when you're done with it, you can move it back into the table. Well, that's kind of annoying to program. and it looks error prone to me. Like you can easily forget to put the value back into the table after you're done. So you want to lend this value, like you want to say, I'm giving you an immutable view into this value v, but it doesn't require a copy. And this can be done with this lend annotation. And here in line 3, this is not a borrow, this is not a copy, and it's not a, this is a borrow, it's not a copy and not a move. And it's actually a pointer under the hood. Like this is it computes the address and gives back the pointer really. But still it's safe, like the nim compiler ensures that this is, you cannot mutate the table as long as the borrow survives. So we now have these lovely parameter passing modes. Here's this tiny intervention and to compare it with C++'s solution. In nim, the default, when you don't say anything, like give me an argument of type t, is actually const tref in C++, unless it's a small object, like an integer or a tuple of an integer or float, then we really pass by copy, because that's what CPUs like. And then we have the sync annotation, which is actually passed by copy in C++. And if you return a lend t, it's like returning a const tref in C++. And finally, we also have var t, which means t is mutable, so that's a reference in C++. And you can also give back a mutable view into something with this var t return type, and then it's a tref return type in C++. Okay, so if nim is C++, why bother with this? Well, nim is not C++. Nim has evolved into these parameter passing modes that are kind of like C++. But nim is still a language of its own. It has a different type system, more inspired by Ada than by C++. The syntax is totally different, and it's much more convenient to work with. It's just that you can say we kind of copied the stuff from C++ that actually works. Okay, so here I have another example. Say I have a function f and it takes a sync parameter string, and by now we know that the string is owned inside the f, but then I do nothing with this x. And the question is, how does this work? And to see how it works, we can ask the nim compiler about expanding what this f really is to us. So in nim there is a couple of different memory management modes. This moves are related to gcorg and gcarg. And so we can ask the system expand this, like there is an intermediate representation of the program, and you can ask the compiler to show it to you. So here what it would show. F was actually transformed into this thing here. So it does destroy the x because it knows it must destroy it, because otherwise there would be a leak. And the lovely thing here is that nim's intermediate language is nim itself. And so with this expand arg command line, you can really understand well what's really going on behind your back if you want to reason about the efficiency of your program. It's much easier to read this nim IR than reading the assembly code. So, but here I have a different example, and here I copy or move this x into G. And what happens here? And so I do use x. And the compiler says, actually, this is a sync operation, like it syncs the x into G. And it also produces, but it doesn't, like, it's a bit hard to understand. It also then says, afterwards, x was moved, and x should be destroyed. And then was moved, and this was moved and destroy pair is optimized away, because these cancel each other out. So what we are left with is you move the x into the G. So this equality sync is actually half of a move. That's actually, like in C++, the sync is basically the first step of a move. And the other step, which is like invalidating the source afterwards, is optional. And the reason for the split is that this way is much easier to optimize, because then these was moved and destroy pairs are close together, and we can make them cancel each other out. Whereas when you put this destructive read into the move operation itself, you need to perform more aggressive inlining to see the same optimization possibilities. And plus, it's less code to write when you're custom sync operations, but we'll get to that. So now we have kind of a feeling that actually there are move operators and destructors involved in them, as like in C++. So here I outline how to implement the sequence in NIM itself via these are called hooks, like equality destroy, equality sync, and equalities copy. 3 resource management hooks that you can use to implement your own custom data types. So I have a sequence. It has a length and a capacity and the data pointer that we've seen in the first example, and it's a pointer to an unchecked array of type T. And the destructor, we first need to say, was this move? Like, is there some data? And if there is, we should destroy all the existing elements. And finally, we should deallocate the memory for this data pointer in line 9. And the move operator is called this equality sync. And here the important thing is that the B, the source, is still immutable. And as I said, it's like the part of a move operation, and the other part is inserted by the compiler if required. And most of the time, moves are from a location that is dead afterwards, so these are dead stores to the source. This was moved and then this is optimized away. But you don't have to implement this sync. Like, if it's not provided and the compiler says I can move this, what it will do, it will call destroy on the destination if there is a value already in there, and then perform a memory copy. So this is kind of optional to program, really. And finally, we see the copy assignment operator. It's spelled equality copy. And here we check. It's really quite close to C++. We need to check for self-alignment. We need to destroy the target first. Then we take the length and the capacity of this B. We need to allocate a new block of memory. That's done in line 8. And then we copy the elements over in line 10. And again, in line 10, we do not know if b.data at position y is used afterwards. So this is a copy and not a move. But if you are unsure, you can use expand arc to see what's really going on. But this you can do more with two sequences than just creating and destroying them or copying them around. You can append an element to a sequence. So this is in line 1 to 4. So we need to resize the memory. Then and now here y is the sync parameter. So in line 3 this is a move. And in line 8, there is this accessor is lending this value to us, so there is no copy here either. And line 10 is again comparable to the add, like this is setting a value at position I, and I must be a natural number, it cannot be negative. And so in line 12 we get the move as well. Okay, so these hooks give us performance, like I have, not in this talk, but there are benchmarks showing that throughput is better, latency is better, and also, of course, memory consumption is better. And it's rare that you win all these three at the same time. So it comes very close to memory management or resource management. But it's safe, like you cannot forget to close a file. You can close your sockets automatically at scope exit, or channels maybe. And you can use them, yes, not just to manage your memory, but to manage your resources, like file handles. These hooks also give us exactly what we need to implement all kinds of exciting stuff. For instance, you can have your atomic reference counting, or non-atomic reference counting if you know that that doesn't cross the thread border. Or you can create copy on write containers that which work like in Swift, where it's close to functional programming, where okay, you can still mutate the container, but the other aliases, there are no aliases to this container, so there's still no spooky action at a distance. It's like a good bridge between the imperative world and the functional programming world. And finally, it's composable. Like your custom containers work with the built-in containers and work with third-party containers because they agree on this interface via hooks. And when I say interface, it's all happened at compile time. Like these hooks do not imply a runtime dispatching mechanism. It's all statically bound and can be inlined and optimized really well. And when you think about it further, when you can do reference counting, you can actually also reason about the aliasings. Like reference counting is really alias controlled. So if if you know the reference count is 1, you know you're the single owner, and you know you can safely store into the memory, or you can safely send it to a different thread. So it's well suited for multi-threading. And finally, these hooks are the foundation of a cost model. So you can, and we'll get a better example, you can reason about what it means when your data structure disappears. Like you can use this for hard real-time systems and soft real-time systems, because with this expand arc feature in the compiler, it can always give you the intermediate representation where the costs are not hidden from you. And you can also then come up and like store this intermediate representation, say, in your tests, so that you can ensure that there is no performance regression when you update the NIM compiler. So here I have another inspiring thought. So this example here is a bit made up, but it shows the ideas. So I have a proc now, or a function, and I create these tuple. In line 2, I say x is a tuple. One value is this high string, the other value is 5. And then, depending on the condition, I overwrite this to a different tuple, or some string here, 80 tuple. And then I output this x. And now, when you run this code, this is what the compiler produces. So it's a bit less readable than I would like, but still quite better than assembly language. So we can see that there are a couple of temporaries created, but only one temporary is actually destroyed in line 17, this temp d_2, which is assigned to in line 14. So it's this dollar operator. So there's this is a two-string operation. So x, which was renamed to a cursor, we'll get to that, is turned into a string for the outputting via echo. And all the other constructions, like I created tuple with the string in there, how come this isn't destroyed? All the other constructions and destructions are optimized out. And the reason here is that the compiler actually produced, did copy-ellsion, and eliminating copies is actually the same as eliminating construction-destruction pairs. So how does this work, this magic? And so the question is, if we have an assignment like destinations becomes source, when do we have to materialize the full copy? Or when can we get away with a shallow copy? And when I get away with a shallow copy, I copy the underlying pointers directly. So it's actually kind of a borrowing operation. So, and the one answer here is when destination or source is mutated after this assignment, then only then you need to perform the copy, otherwise you don't. So you get this compile time copy on write optimization. And when you look at the program, actually X is mutated, but X is mutated completely and not just fields in X. So there's some really smart optimizer going on here. And well, of course, the downside is these intelligent optimizations might usually imply that the code is kind of hard to reason about when you actually care about the performance. When you don't care about the performance, it's great because then you can simply write your code, use these value-based data types, and end up with a very, very fast solution which is readable and in the high level description of the problem. But when you do care about these low-level details, you can ask the compiler, what did you do with this function here over there? What is its IR like? And it will tell you, and then you can see, okay, this is really cheaper than I thought it would be. So I can leave the program in the high-level style and not worry about it. Okay, so yeah, copy-ellsion is really a form of borrowing. Here's a different example. In line, so I start with a sequence of strings and I pass an integer index, and then there is some idea here that I do not want to evaluate this s at position 0, which would be s at position y, by the way, s at position 0 all the time. So I use this v then, and then I use it again, and so it's a sequence of strings. It's a string. This should be an expansive copy, right? Well, no, because s is a mutable parameter, so we know it's not changing, and we know that v is not changing because it's a local variable that we can reason about. So again, there is no copy here. It's like borrowing, automatic borrowing, except that you don't need the pointer annotations, like no address or pointer dereference inside. So the program can stay in this high-level description of what it needs to do and trust the NIM compiler to do the right thing. So coming back to this question in the beginning, what is actually NIM? NIM means optimizations that you can rely on. See this expand arc feature. Optimizations that work with custom resource management hooks. So and finally, it's kind of a search for and an answer for the axioms of memory and resource management. Thank you. And now I'm online to reply to your questions.